Okay, good morning, everyone. Continue our discussion about the fluid flow. And before I continue the lecture, I will a bit review what we have discussed in our previous class. So basically, fluid is considered to be flowing when they have continuous deformation. And these continuous deformations are, for the fluid flow, is generally caused by these four types of force. So tensile force is the force that pulls the fluid. So it means the force comes from the front part of the fluid flow. And then opposite of the tensile force is basically the compression force, or we call it also the pressure force. So the force comes from the back part of the fluid flow. And then the other types of force that cause the continuous deformation is what we call the shear force. The shear force comes from the, how do you say, the surface. Yeah, the surface. It means if the fluid is flowing through a cylinder pipeline, so the surface will be the surface area, luas selimutnya. Yeah, that's the shear force. Whenever the shear force is applied on the fluid and the fluid is start flowing, because fluid are considered as layered. It's not one big sum of the compound. You can consider fluid as layering part. So each layer of the fluid will give resistance to the shear force. Yeah, for example, near the pipeline, near the inside wall of the pipe, the fluid will give resistance. This resistance called the friction force. So if this 1, 2, 3 types of the force are causing the fluid to flow, the last types of the force will resist the motion of the fluid. Okay, this is the types of forces that act on the fluid, causing the continuous deformation. And based on the velocity, depending on the velocity, the fluid will undergo different types of flow, or we call it flow regime. Ya, jadi berdasarkan kecepatan akan ada yang namanya rejim aliran atau jenis aliran. The extreme one, the slowest one, because of the very low velocity, the flow regime will be laminar flow. On the opposite, if the velocity is very, very high, the flow regime will be the turbulent flow. The characteristic of laminar and the turbulent flow, we have discussed it on our previous class. And this is the parameters, the important parameters that we will often encounter where you deal with the fluid mechanics calculation. We call it Reynolds number. So Reynolds number is basically the ratio. It's the comparison. There will be no units of Reynolds number. It's the comparison between the inertial force, which force that causing the fluid to flow. So the higher inertial force, the flow will be, the continuous deformation will be higher. And it's divided by the viscous force because of the viscosity. This is the force that resists or against the fluid flow. So the calculation of Reynolds number will be depending on these parameters, the density of the fluid. Yeah. Please also remember, whenever you encounter some equation, once you need to understand the meaning, the physical meaning of the equation or the meaning of the parameters. Like this one is the physical meaning. And the second one, you need to pay attention to each parameters considered in that equation. So for Reynolds number calculation, the parameters will be fluid density with the unit of kilogram over cubic meters. And then the pipe diameters, internal pipe diameters, so the unit will be meters. And then average fluid velocity or average linear velocity, the unit will be meter per square. And then viscosity, fluid viscosity, the unit will be kilogram over meter square. You need to check whether the whenever you encounter the equation, please check the parameters and each of the unit, and then you do the unit checking whether the unit is already correct. So it's supposed to there is no unit for Reynolds number. So between the numerator and denominator should have a similar unit. Okay, this is the Reynolds number. By calculating the Reynolds number, we can classify the flow regime. Yeah, if the Reynolds number are quite small, so the flow regime will be laminar. Vice versa, if the Reynolds number is quite high, then the flow regime will be turbulent, and in between we call it transition regime. Okay, we have discussed what is the application, but later we will discuss further this application. And on our previous class, we have also discussed, especially for the fluid, if the fluid are flowing is flowing to the pipeline, depending on the size of the pipeline, and depending also on the velocity of the fluid, the volumetric velocity for the fluid, it might not fully fill the pipeline. Ya, jadi bergantung pada ukuran pipanya. Jadi khusus untuk cairan ya, untuk fluida cair bergantung pada ukuran pipanya dan bergantung pada kecepatan alirnya, laju volumetrik alirannya. Ketika mengalir di dalam pipa, fluida cair itu belum tentu akan mengisi pipa secara penuh. Ya, depending on the size and depending on the flow rate, the liquid will not always filling the pipelines. So in the case when the fluid are not fully filled the pipeline, you need to determine what we call equivalent diameters or hydraulic diameters. Yeah, so this is the same, equivalent diameters or hydraulic diameters. It will be 4 times hydraulic radius. So it bit different with the concept of the diameter and the correlation between diameter and radius that you have known before. The simple one is diameter is 2 times radius, right? But for hydraulic, it will be 4 times. And what will be the definition of hydraulic radius? It will be the cross area divided by weighted perimeters. Weighted perimeters is the cross-section area that will be in contact with the liquid. Ya, jadi yang namanya weighted perimeter atau perimeter terbasahi itu adalah bagian dari penampang yang terbasahi atau berkontak dengan cairan. It will be depending on the cross-section shape of the pipeline and how much the liquid filling the pipeline. Ya, jadi weighted parameternya itu akan bergantung pada bentuk penampang pipanya dan seberapa penuh si cairan tadi mengisi pipa. So previously we have see the this case. We have 3 cases with the rectangular shape of pipeline. So each case will have different value, different calculation of the equivalent diameters or hydraulic diameters. Okay. Also, if you have this one, do you know where or do you have any idea where you might find this type of annulus pipe? Ini namanya adalah pipa anulus. Pipa anulus itu adalah pipa ganda ya, pipa rangkap, di mana yang satu kecil ada di dalam yang besar. They will have the same center point. Okay, where do you can find this type of arrangement? Okay, let me ask you. Okay, I think you should rename into student number and name so I can see you in apa ya, urut gitu ya. The name is according to the student number. Okay, let me ask Muiz Firdaus. Are you there?
Hello, hello.
Yes, this is the name of this arrangement is endless pipe. Okay, do you have any idea where you can find this kind of arrangement? In what kind of equipment? Right. Can you name examples where you can find a double pipe with the annulus arrangement?
I'm not sure, sir.
Okay, I'll ask other. Dimas, Aditya.
Yes, sir.
Yes.
I still quite don't get it, sir.
Okay. Any other student might want to try to guess? Double pipe arrangement can be found in what type of equipment?
Sir,
Yes.
Condenser.
Yes, condenser, correct. Condenser, or in general type, in general term, we call it heat exchanger. Yeah. Later, as a chemical engineering student, I think you should familiar with the heat exchanger. There are various types of heat exchangers. Heat exchangers can be used to increase the temperature of the fluid, where we call it heater, or maybe to decrease the temperature, or maybe to change the phase of the vapor into the liquid. So you reduce the temperature, we call it condenser, but basically it's heat exchanger. And one type of the heat exchanger is the shell and tube heat exchanger, or double pipe heat exchanger. So the cross-sectional, the simple one will be like this. The double pipe will be maybe the cold one, the cold fluid, or no, it's kebalik, sorry. So the hot fluid can runs through the smaller pipe, and the cold fluid can flow to the bigger pipe. So if we see at the point with the point of view of the cold fluid, it will be flowing to this area, right? So later, if you want to do calculation on the cold fluid, the hydraulic diameter will be influenced by the weighted parameters. So the weighted parameters will be the inner diameter of the larger pipe, right? So this one is larger pipe, the inner diameters plus, so it means the weighted parameters will be the circumference of the inner diameter, yeah, plus the circumference, inner diameter of the large pipe, and the circumference of the smaller pipe, outer diameters. This will be the outer, this will be the inner. Because in the real case, pipe will not have will have certain amount of thickness, right? So we have to consider the inner and outer diameters. Okay, this one. So basically, which one is 1 and which one is 2? Yeah, basically, once it should be the D1 is the outer diameter of the tubing, and D2 is the inner diameters. Inner diameters should be the larger pipe, and outer diameter should be for the smaller pipe. Okay, any question about the calculation of the hydraulic diameters or the calculation of the Reynolds number? So for this Reynolds number, this one, right? So this one should use the diameter, hydraulic diameters. So if you encounter the case where you have like this endless pipe, or you have a case like this one, So Reynolds number should be using the hydraulic diameter, equivalent diameters. Ya, jadi jangan langsung, don't directly use the value of the pipe diameters. Okay, previously I told about the wall thickness. So when you buy a pipe or tubing, smaller pipe, namely tubing, ya. Jadi kalau mau beli pipa atau tube tabung, basically the size that the pipe is not the equipment or the thing that you customize by yourself. Yeah, during building a plant, a chemical plant, when you need to flow the liquid or flow the gas, flow the raw materials, you need to buy a pipe, right? You need to install a piping system. And when you buy a pipe, it's not customized. It means certain types of materials will have certain standard of pipe size. Ya, jadi pipa itu secara umum kalian tidak pesan gitu ya. Pesan itu maksudnya, oh pengen pipa diameter sekian, pengen pipa terus bikin dulu gitu ya. Enggak. Tapi berdasarkan bahannya, depends on the materials, they will come in certain size, and it was called nominal pipe size. Ya, jadi kalau beli pipa itu pasti nanti akan ditanya pipa ukuran berapa, 1,5 kah, 2 kah, 3 kah? That represents the nominal pipe size in inches. So the unit will be inches. Then how to know the thickness? How to know the real diameters? How to know the inner diameters? How to know the outside diameters? Normally, each pipe nominal size will have what we call schedule number. Ya, jadi untuk membedakan pipa yang sama-sama 1,5 atau sama-sama 2 inci, tebelnya itu berapa, itu adalah menggunakan schedule number. Ya, there will be 1.5 pipe inch with schedule number 40 and 1.5 with schedule number 80. The higher the schedule number, you can see from this table, the wall thickness will be higher. It will be thicker. Yeah. So pipe with higher schedule number will have thicker wall thickness. What is schedule number actually? Basically, this is the standard from mechanical engineers that represents how strong the pipe to sustain certain pressure. Ya, jadi pada dasarnya angka ini tuh dibuat ya oleh mechanical engineer untuk mengkuantifikasi, untuk membedakan seberapa kuat dia menahan tekanan. Ada rasionya, tapi itu hitungannya saya juga nggak hafal. You can check later, maybe you can Google it by yourself. But the higher the schedule number, wall thickness will be higher. So the outside diameter will be the same. Yeah, the same nominal pipe size represent the same outside diameters, but the value will not be the same as the nominal pipe size. For example, the nominal pipe size is 1.5, the outside diameter will be 1.9. And actually, this will be depending on the pipe materials, because pipe can be made from maybe you already know, right? Or can you guess what kind of materials that normally used to build a pipe? Pipa itu dibuat dari apa? Apa saja? Galang.
Stainless steel, sir.
Okay, stainless steel. Any other materials that you know? Why it's not?
Inconel, sir.
Sorry.
Inconel.
What is it?
It's a.
Or you can mention in Indonesian word if you know the
It's another alloy, sir. It's another steel alloy in Cornell. I forgot what it's really made of, but yeah,
In
that's
Cornell,
another
is it?
alloy. Yeah, in Cornell.
Oh, I thought it's like nickel alloy, I think.
Oh yeah, sir. Yeah,
Yeah,
no,
okay.
sorry. Nickel alloy.
Okay. Beside that, maybe from other student, apakah selalu terbuat? This is types of steel, right? Logam.
PVC, sir?
Sorry?
PVC?
Yes, that's the common types of materials, right? Polyvinyl carbon. And then it can also be made from concrete. The metals, yeah, it's not only steel, but sometimes it made from copper as well. So the outside diameters will be depending on the nominal size and also depends on the material of the pipe. But the one in common is the higher the schedule number, then the higher the wall thickness. It means it will have smaller inside diameters and so on. Okay, where you can find these tables, you can get from the handbook or the equipment or the pipe specification sheet, pipe specification sheet. Okay, this one is also the case for this is for the carbon steel, right? Carbon steel or stainless steel, they will have different schedule number. And then for each schedule number, you can check from this table how much is the wall thickness and how much will be the inside the diameters. Don't forget to calculate inside diameters. If you only have the outside diameters and wall thickness, inside diameters will be outside diameters minus 2 times wall thickness. Karena diameter ya, bukan radius. Yeah, so the inner diameter will be the outside diameter minus 2 times the thickness. So inside diameters will be the value that you need to use to calculate the Reynolds number. In general, yeah, in general, when you do the calculation of Reynolds number, you need the value of diameters, right? So this will be using the inside diameters. Kecuali yang tadi, except for the case for the annulus that we have been discussed before, for the smaller tube, you need the value of outside diameter. Okay, any question until this point? Okay, then I will continue to the next part of the lecture. That we will discuss about mass balance in fluid flow. Yeah, I think you already or now in third semester, I think you study the mass and energy balance, right? The same semester with the fluid mechanics, right? So can you tell me the general equation of mass balance?
Is it input equals to output, sir?
That's the very simplified one. The general one, accumulation will be anyone know? Yasmin.
Yes, sir.
Do you remember or do you already learn about the general mass balance equation?
I don't remember us learning about the general equation, but
yes.
Yeah. I have no clue, sir.
Okay. Actually, what Azra told is a bit, yeah, it's correct. Input will be equals output, but it will be the very, very ideal case. So maybe you have not learned in the mass and balance class. Sorry, mass and energy balance class. But generally, the accumulation for the mass balance equation, accumulation of mass will be the same as mass input minus mass output plus mass generated minus mass consumed. Ya. Jadi ini persamaan generalnya, umumnya. Persamaan awalnya gitu ya. Jadi kalau ada, if you have a system, you have like this one, this is input, this is output. Reaction might occur, right? We talk about system in general where maybe you have a reaction. So, as the mass conservation law, the first is mass can neither be created or destroyed. I think you already learned this concept in your high school on INTPB. And then, if we have a reaction, then the mass of the product will be the same, will be equal to the mass of the reactant. It means if 1 kilogram of the reactant is react ya. Jadi kalau ada 1 kilogram reaktan bereaksi, maka produknya kalau secara ideal there will be 1 kilogram as well. In terms of mass. However, in some system, mass is not only generated, but mass will be also consumed. So if there will be no, if there is imbalance of mass generated and mass consumed, it will create what we call accumulation of mass. Ya, jadi secara umum nanti kalian di kuliah neraca massa akan belajar lebih detail sih. Tapi intinya adalah kalau ada sistem masuk, ada sistem keluar, ada reaksi, maka laju akumulasi itu akan sama dengan laju masuk dikurangi laju keluar, ditambah yang terbentuk dikurangi yang terkonsumsi. There will be it is the general equation of mass balance. Okay, the same case for the fluid flow. Okay, this one is the general case. Yeah, flow rate of mass flowing into the system minus flow rate of the mass flowing out of the system. So this is the input. This is the output minus rate of generated mass in the system. Ini I think I have to correct the. Okay, please take note. This is plus. This is plus. Plus rate of generated mass in the system minus rate of the mass consumed in the system will be equal to accumulation. Accumulations mean change of mass of the time. Ya, jadi this one, if you note it with this one, dm over dt. So if this 4 component, right, input minus output plus generated minus consumed is not balanced, means it's not zero, then we say we have mass accumulation in a system. Ya, jadi kalau ada ketidakseimbangan ya antara yang masuk dengan yang keluar, dengan yang dikonsumsi dan yang dihasilkan, itu akan terjadi yang namanya akumulasi. Ada akumulasi itu berarti ada perubahan massa terhadap waktu. Ya, akumulasi massa itu artinya ada perubahan massa terhadap waktu. the more ideal one that we say the condition is steady state. Have you learned this term in mass energy balance class? Steady state? Sudah belum?
I think, sir, maybe in another class too, not mass balance.
I mean, in your class? I think you all are in the same class, right? In mass and energy balance.
Yes, sir.
Yeah. Have you learned about the steady state? Lydia. 1 to 6. Have you learned about the steady state, Lydia?
I don't think it's in mass balance, sir. I think it was in PTK.
Oh, in PTK. PTK, okay. You have PTK in this semester as well, right? But you should learn this one also in the mass balance class. But maybe the lecture is not there yet. So when there is no accumulation in the system, there is no dm over dt, we call it steady state system. Atau kita sebutnya tunak kalau bahasa Indonesia. Jadi kondisi steady state. Kondisi steady state system means no accumulation. So the rate of accumulation will be 0. Yeah. This one equals 0. We call it no accumulation. Steady state means no accumulation. Okay. For the simpler case even more, to simplify the case even more, and it is the case of the flowing fluid, there will be no reaction, right? If just water flowing inside the pipe, there will be no reaction. So it means rate of generated mass in the system will equal 0. And then rate of mass consumed in the system will equal 0 as well. So the component of flowing fluid, the component of mass balance of flowing fluid is only flow rate of the mass flowing into the system and flow rate of the mass flowing out of the system. Ya, jadi di kasus fluida mengalir karena tidak ada reaksi, kemudian kondisinya dianggap steady state, tidak ada akumulasi, maka komponennya tinggal input dan output saja. And there, it will be equals 0. That's why input will be equals to output. Okay, I hope it's easy to understand. If you have any question, just open mic and ask. Or you can write in the chat, you can raise your hand. Okay, any questions so far? Okay, so okay, don't get confused with the equation. This is the mathematical equation that represent what I have said before about accumulation. Yeah, this is the accumulation, dm over dt, and you still remember, right? Mass will be density times volume, right? This one is kilogram, this one is kilogram over cubic meters, this one is cubic meters, so it should be the same. So dm over dt will be equals this one. And for general case, especially if we are dealing with gas, you still remember that the characteristic of the gas, they will have, for the liquid, it will be constant, right? if you have a change in temperature and change in pressure, density of liquid is generally constant. But for the gas, it will be change. So density in this equation for the gas will not be a constant parameters. Volume, of course, it won't be the constant parameters. For the liquid, both are constant. Ya, jadi kalau untuk cairan, ketika tekanan dan temperatur berubah, density itu relatif tetap. Karena massa itu tetap, berarti volumenya juga tetap. Sehingga dm per dt-nya, ya, Anda bisa anggap rho dan V sebagai parameter yang tetap. Tapi untuk gas, karena density itu berubah, massa akan tetap. Ya, hukum kekalahan massa. Ketika densitasnya berubah, volume akan berubah. So, the notation of mass accumulation rate can be divided into this one. This calculus, right? U aksen T tambah U T aksen. If you have two parameters, you divide it, you derive it, and then it will be this one plus this one. And if the rate of accumulation is 0, ya, ketika akumulasinya sama dengan 0, ya, bagian ini sama dengan 0. Later, we will use this equation when we deal with the with compressible fluid. Gas is compressible, so the density is not constant. So we will deal this equation more when we discuss about the compressible fluid. But for liquid, the incompressible, just assume dm per dt, and then in steady state condition, it will be 0. Input will be the same as output. Okay, so for example, liquid is flowing to the pipe with this kind of arrangement. This is the inlet cross-sectional area, A1, and this is the second one, the outlet, A2. So it will flow from point 1 and comes out from point 2. Based on the equation that or the mass balance that we have discussed before, since the condition is steady state, input will be the same as output, right? So this is the steady state mass balance. The mass flow rate at the inlet will be the same as mass flow rate at the outlet. Mass, tadi massa apa? Densitas kali volume. This one will be cross-sectional area times velocity. Ya, ini kilogram over cubic meters. Sorry, this is a cubic meters. This is cross-sectional area. U is linear velocity. So this one should be like this. This one is kilogram per second. And then this one is cubic meter per second. So the equation become this one. Ya, jadi dalam persamaan ini, in this equation, rho times A times U, the unit will be kilogram per second. or mass over time. As the input will be equal output, then this multiplication at point 1 will be the same as this multiplication at point 2. It will be constant, and we call it equation of continuity. Okay, for liquid, the incompressible fluid, the density at point 1 will be the same as density at point 2. So you can also say that the volumetric flow rate at point 1 will be the same as volumetric flow rate at point 2. Yeah, this is the volumetric flow rate. Or we can, the notation, we can use V with the dot or Q. Okay, any question until this part? I think this one is a bit mistake. It's not mass per density. You can, so the unit should be this one. So if this one should be, yeah, I think this one. So mass flow rate, kilogram per kilogram per second divided by kilogram per cubic meters. So becomes cubic meters per second. Ya, jadi yang ini ada titiknya ya. Laju alir massa dibagi dengan densitas. Okay, any question? So basically, you can say that the volumetric flow rate Q1 equals Q2 equals Q. It's only happen when the fluid is incompressible. Ya, jadi debit masuk akan sama dengan debit keluar. Volumetric flow rate masuk sama dengan volumetric keluar. Itu hanya kalau fluidanya incompressible. It means it only happen when the density is always constant. If the density is not constant, then you can use this one. You can only use this one. Yeah. This one is applied for the steady state condition and for any types of fluid, whether is incompressible or compressible. Ya, massa masuk, laju massa masuk sama dengan laju massa keluar itu persamaan umum, asal kondisinya steady state dan tidak ada reaksi ya. Jadi laju alir massa masuk sama dengan laju alir massa keluar. Kalau densitasnya tetap, the fluid have the constant density, incompressible fluid, then you can change into Q1 equals Q2. But if the density is not constant, you can use this one. Okay. Okay, I think this one is not. Don't be intimidated again with the equation. However, you need to understand that when when the liquid or gas flowing into the pipe arrangement might not have similar diameters. Then the pipe will not might not have the same height related to the baseline. Ya, jadi ketika fluida itu mengalir, pipanya belum tentu ukurannya sama terus. Pipanya belum tentu selalu lurus, gitu ya. Kadang belok, kadang naik, kadang turun. Ya. However, along this cross-sectional area, along the different height, the continuity equation is still applied. Persamaan kontinuitas tadi, persamaan raca massa tadi masih tetap berlaku. If you have a constant density fluid, then the constant volumetric flow rate is also applied. So this one, Q will always be constant as long as incompressible. The one that changes is A. A is cross-sectional area. So if the fluid is flowing to different cross-sectional area, then it will have change in linear velocity. Ya kan? Kalau diameternya berubah, cross-sectional areanya berubah, sementara debitnya atau volumetric flow rate-nya itu konstan, berarti U-nya, kecepatan liarnya akan berubah. That's the one that you have to understand. The constant one is always, of course, mass. Mass flow rate will be constant, density constant, then volumetric flow rate will be constant. If it is flowing to the different cross-sectional area, then A will be different and velocity will also be different. Okay, sometimes you can express the mass flow rate in terms of mass over area. Yeah, this one a bit you need to be careful when later maybe you read a textbook, you find this one. If the G will be this one, what will be the unit? I want to check your understanding, whether you understand what I have been saying or not. Alika.
Yes, sir.
What will be the unit of m dot?
Is m dot to the power of 3?
The unit, satuannya.
Oh, yeah. Satuan.
Mass flow rate, what will be the unit?
Meters.
Mass flow rate.
Oh, mass flow rate. Oh, is it meters in
wake up.
per second?
Yes, sorry?
Kilogram per second.
Kilogram per second. How about the area? Cross-sectional area.
Meter squared.
Meter squared. Yeah. So sometimes mass flow rate are expressed in these parameters. Mass over time over area. This one, we call it mass flux. Ya, jadi please try to memorize. Flux is basically flow rate. Yeah, rate means if you heard terms rate, heart rate, flow rate, it will be depending on the time, right? So mass flow rate, kilogram per second, divided by area, we call it mass flux. So this one is basically flux. Ya, this one. Ya, jadi jangan bingung. Maksud di sini adalah flux. Mass flow rate divided by area. It means mass flux will not always be constant, right? Karena yang konstan itu ini. Yang konstan itu selalu massa per waktu atau massa. Itu akan selalu konstan. Tapi kan area bisa nggak konstan ya. Karena area yang bisa nggak konstan, maka velocity tidak konstan. Karena area bisa tidak konstan, maka mass flux juga tidak konstan. Okay, I hope you get the concept. So the one that always constant is mass or mass flow rate. If the density constant, then volumetric flow rate is also constant. Only when the density is constant. Okay, any question? Okay, then you can see from these figures as well, if you have branch of pipe, yeah, for example, from pipe with the bigger diameters, A1, and the velocity U1, and then divided by two branches. First with A2 and U2, and then this is A3 and U3. The one that always constant with always this one, because input will be same as output. Yang memenuhi ini itu hanya laju massa atau massa. Kalau densitasnya konstan, berarti debit juga konstan. Ya, so mass will be density times volumetric flow rate. If the density constant, then you can cancel out the density, right? So Q1 will be equals Q2 times Q3. Dikoreksi ya, ini jumlah. Okay, you need to listen to the class because some correction will be made throughout the slide. So if later you reread the slide or recheck the slide and you find the equation is a bit weird, you can discuss back in the class, or you can ask me later. Okay, this is the concept. So input will be same as output in terms of mass, and then if the density is constant, input will be equals as output in terms of volumetric flow rate. Volumetric flow rate is cross-sectional times linear velocity. Okay. Okay, I think we will have 5 minutes, 10 minutes exercise. Please check your slide, or you can this one, but I will make some correction first. So a tank is being filled with water through D1. One is here. With the average speed is velocity. Yeah. So at this one, the velocity will be 5 meters per second. And D2, 2 is this one. With the volumetric flow rate is 0.012. So this one is Q2. And the diameters will be 50 millimeters. Okay. If the level in the tanks remains constant, yeah, this one constant, please calculate the velocity at point 2, and this is D3, and the velocity at point 3. Apa artinya ketinggian konstan? What is the meaning of the level in the tank remains constant?
Zero accumulation.
Zero accumulation, correct. And then it will be achieved by relating to these three flow.
Constant rate, sir?
Yeah, can you speak louder, please?
Constant flow rate.
Constant flow rate? What do you mean by constant flow rate?
Like it does not change, so it keeps on being the same.
Gimana? Please, can you rephrase again? Sorry.
So it's like it's going in at the same rate, like at the like different time.
It's going in at the same rate at the different times.
Yeah.
Okay, and then the correlation between the flow rate at point 1, 2, and 3.
What,
if you want to have this constant height of water, it means
there is nothing. It's the same, continuous.
Of course, it will continue. It's flowing, right?
So,
I think you need to rephrase your sentence in more clear way.
I understand, but I can't say.
Yeah. Okay. Any other? Maybe other student can help. Joshua.
Yes, sir.
How to achieve constant height? Yeah, constant level of liquid.
By having the same volume rate of input and output?
Yeah, correct. So the water flowing into the tank has to be the same as water flowing outside the tank, right? Into the tank will have to be the same as out the tank. It means this one should be equals this one. Karena kalau enggak, kalau yang masuk kelebihan, maka dia akan meluap. Kalau yang keluar kelebihan, maka tingginya akan turun. Yeah. So if the flow rate, the input flow rate is higher than output, then the water will be overflow. The head will increase and then it will be overflow. If the output rate is higher than the input rate, then the head will be reduced and yeah, it's keep reducing. Okay, so by using this information, I want you to calculate. I think until now is, what time is it? 11:01. So please state your answer. Yang ditanya U2 dan U3. What will be the unit of speed or velocity? Anyone? Wake up, please.
Meter per second.
Yeah, it's meter per second. So please calculate velocity at point 2 and velocity at point 3. I make some adjustment, right? So 0.012 is flow rate at point 2 and 60 millimeters is diameter at point 3. So please calculate and give your answer by 11:10. I will randomly ask student. Okay. Okay, it's already 11:10, so I'll ask one student. Dana, I Gusti Ngurah Waradana Nugraha 127.
Yes, sir.
Okay, how much is your answer?
My U2 is 6.112 meters per second.
Just a sec, okay?
But I'm kind of confused with my Q3. My Q3 is 6.466 meters per second.
6.47,
466.
okay. Okay, thank you, Dana. I'll ask other Azra.
Hello, sir.
Yes,
For my U2 is I got 6.11, sir.
okay, the same.
And for U3 is I got 6.436.
6.44 then.
Yeah.
Okay, I think it should be. I think you got different numbers due to maybe some round up of the numbers. Should be okay. Anyone got different numbers from this answer? Anyone else? Or the same? Ahdan 125. Ahdan Prawira Irfansyah. Are you there?
Yeah, yes, I am, sir. I myself got the same with Azra. So the U2 is 6.11 and the U3 is 6.44.
Okay. Okay. No problem, Sid. I think you already got the concept. Then for others that still do not get the same answer or maybe got the very different answer, you can discuss among you. And then later, if you still have a question, you can ask me. Okay, let me continue then. Just a sec. Okay, for this exercise, I want you to try by yourself first at home. If the previous case, the water level is constant, right? So just input will be equals output, and it means there will be no accumulation at the previous case. For this case, the water level will be will change. So it's not constant. It means you will have accumulation. And if velocity at point 2, so the other parameters, of course, beside that you have calculated, right? So the data for point 1, point 2, point 3, the same. And then if you have speed at point 2 will equals 8 meter per second, then please calculate the accumulation of water in terms of water level. So not dm per dt. Previously, accumulation at example number 1, this one, accumulation will be equal 0. What is m in this part? Mass. How to calculate mass if you have a tank? Should I ask? Oke, siapa yang belum ditanya ya? Oke, Jilan, are you there?
Yes, sir.
Yes. How to calculate mass if you have a tank with diameter D and H and height H. Kalau diameternya D, tingginya H, how to calculate mass of water inside of the tank?
I think we would use the volume of the cylinder then.
Volume times? Mass is kilogram, right? This is
times the density.
Times density. Yeah, correct. So you need to know the value of the density. If water, then you can just use 1 kilogram per liter or 1000 kilogram per cubic meters. Then volume, then you can get the correlation of the cylindrical volume, right? Water PD square times height. Ya, volume kan luas alas kali tinggi ya. Luas alas lingkaran itu 1/4 pi kali diameter kuadrat dikalikan tinggi. So you can use this correlation to calculate dm over dt. Yeah. So the accumulation you need to calculate are in terms dh over dt. Because diameter is constant, yeah, diameter is constant, and then density is constant. Both are constant. So it's assumed that this one. Okay, how to calculate? You already calculate that in order to achieve no accumulation, yeah, in order to achieve constant height, you get this value, right? U2 is this one, U3 is this one. Then replace U2 by 8 meter per second. Sorry. If the U1 is this one, U2 is this one, and U3 is this one, please calculate the dH over dt. Okay, please do it at home, and then later we will discuss in our next class. Okay, this one is also example of continuity equation. So for the real case, a bit of real case, this is the crude oil, minyak mentah. So the petroleum crude oil having the density of 892 and then flowing to this pipe arrangement. You can see from this arrangement that the pipe have different diameters along the pipeline. So first, at the first part, it will be 2 inches of diameters. Yeah, 2 inch schedule 40. And then it will goes to the bigger pipe, 3 inch schedule 40. This is the nominal pipe size, the one that I have told you before. Jadi yang diameter ini bukan diameternya yang nyata ya, ini diameter nominalnya. Schedule-nya 40. And then after that, the pipe is divided into 2 pipeline with the same diameter, which is 1.5 nominal size. Okay. The total rate is 1.38 times 10 to the power of minus 3 cubic meters per second. So by knowing the unit, what does it mean by total rate? Kalau melihat satuannya, total rate ini maksudnya apa? If you know the unit, yeah, because the parameters term sometimes is different. Sometimes it's just called rate, total rate, sometimes it's mass rate, sometimes it's volume rate. So the total rate here is volumetric rate. Q. Yeah, it is written total rate. Don't get confused, just check the unit. So the Q will be this one. And then it's flowing. Because we can assume the flow is steady state. So it means Q1 will be equals Q2 will be equals Q2 times Q3, right? Because it's divided into 2 pipes. Okay, then you can calculate the mass flow rate in pipe 1. This is this one, kilogram per second. The average velocity in pipe 1 and pipe 3, this is meter per second. And mass velocity, basically kilogram per second per square meters. Yeah, so you can check, you can try to do the calculation first, and you already have the solution here, then you can check. First, you need to convert the nominal size into the actual size. Yeah, for example, for 2-inch nominal size with schedule 40, the diameter, inside diameter will be 2.067 in inch. Then you need to convert to square meter. You can do the same for the second diameter and the third diameter. And the total mass flow rate is just the volumetric flow rate times density. You get the mass flow rate. Yeah. Mass flow rate will be volumetric flow rate times density. Okay, since at the pipe 3, it's divided equally, then the mass flow rate at the pipe 3 will be half of the mass flow rate at pipe 1. Then velocity is basically mass flow rate divided by what? Key, right? And key is the same as density times this one. Okay, then you get this value. Okay, for part C, mass flux, kilogram over second over square meters, then just mass flow rate divided by area. Okay, I'll remind you again, then every time you do the calculation, please double check the unit. Is already confirmed or not? Yeah. Okay, any question until this part? Ada yang mau bertanya? Ini diem, paham lah ya maksudnya. Okay, please redo the exercise again because by doing the exercise, it helps you to understand the concept. Do the exercise as much as possible, not to memorize the question, ya. Jadi mengerjakan latihan itu jangan untuk menghafalkan soal, but it helps you to understand the concept because the soal can be varied many forms, in many forms. Okay, then I'll show you about the energy balance, but maybe for some break for a bit, I will show you some video about the Bernoulli equation because the energy balance will be later correlated to Bernoulli equation. Okay.
Velocity Stream for sponsoring this video. Watch thousands of documentaries and get access to Nebula for free when you sign up using the link in the description. Bernoulli's equation is a simple but incredibly important equation in physics and engineering that can help us understand a lot about the flow of fluids in the world around us. It essentially describes the relationship between the pressure, velocity, and elevation of a flowing fluid. It has countless applications. We can use it to explain how planes generate lift, or to calculate how fast liquid will drain from a container, for example. We'll explore these applications and a few more later on, but let's start by reviewing the equation itself. It was first published by the Swiss physicist Daniel Bernoulli in 1738, and it looks like this. The equation states that the sum of these three terms remains constant along a streamline. Each of the terms is a pressure. The first term is the static pressure, which is just the pressure P of the fluid. Then we have the dynamic pressure, which is a function of the fluid density, ρ, and velocity, v, and represents the fluid kinetic energy per unit volume. And the last term is the hydrostatic pressure, which is the pressure exerted by the fluid due to gravity. G is gravitational acceleration, and h is the elevation of the fluid, which is just its height above a reference level. This is the pressure form of the equation, but it can also be presented in the head form and the energy form. We can think of Bernoulli's equation as a statement of the conservation of energy. It says that along a streamline, the sum of the pressure energy, kinetic energy, and potential energy remains constant. This is really valuable information that can help us analyze a whole range of fluid flow problems. The equation does have a few limitations, which I'll cover later on in the video. But for now, the important thing to note is that it can only be applied along a streamline. We can define a streamline in steady flow as the path traced by a single particle within the fluid. Or more technically, as a curve that at all points is tangent to the particle velocity vector. Let's look at an example where we apply Bernoulli's equation to flow through a pipe which has a change in diameter. We want to use the equation to see how the pressure changes as the flow passes from the larger to the smaller diameter. Bernoulli's equation is usually used to compare the flow at two different locations, so we can rewrite it like this, with points 1 and 2 both being on the same streamline. There's no significant change in elevation between points 1 and 2, so the potential energy terms cancel each other out. And if we put all of the static pressure terms on one side, we get this equation for the change in pressure. If we assume that the fluid is incompressible, the mass flow rate at points 1 and 2 must be equal. This gives us what's called the continuity equation, which is just a statement of the conservation of mass. Mass flow rate is equal to the product of the fluid density, the pipe cross-sectional area, and the fluid velocity. So we can rearrange the continuity equation to obtain an equation for the velocity at point 2. The cross-sectional area, A2, is smaller than A1, which means that the velocity of the flow increases as it passes into the smaller diameter pipe. This is quite intuitive. By substituting this equation for V2 into Bernoulli's equation, we can see that since the velocity increases between points 1 and 2, the pressure between both points must decrease. This concept that for horizontal flow an increase in fluid velocity must be accompanied by a decrease in pressure is one way of formulating what we call Bernoulli's principle. It can seem counterintuitive because people often expect an increase in velocity to result in a corresponding increase in pressure, but it makes sense if we think about the conservation of energy. The energy required to increase the fluid velocity comes at the expense of the static pressure energy. Bernoulli's principle shows up in a lot of different places. We can use it to help explain how plane wings generate lift. Fluid flowing over an airfoil travels faster than fluid flowing below it. According to Bernoulli's principle, this creates an area of low pressure above the airfoil and an area of high pressure below it. And it's this pressure difference that generates lift. I'll cover lift and drag forces in more detail in a separate video. Bernoulli's principle also explains how Bunsen burners work. When the gas valve is opened, gas flows into the barrel at high velocity. Following Bernoulli's principle, this high velocity creates an area of low pressure in the barrel, which draws air in through the air regulator, allowing for more complete combustion of the gas. Several different flow measurement devices rely on Bernoulli's equation to determine the velocity of a flowing fluid. The pedostatic tube is one such device. It's often used in aircraft to measure airspeed. Here's how it works. If we place a tube into a flowing fluid, like this, and we attach a pressure meter to the end of it, the meter will measure the pressure at the end of the tube. At this point, the fluid velocity is reduced to zero, so it's called the stagnation point, and the pressure measured by the meter is called the stagnation pressure. We can apply Bernoulli's equation between an upstream point and the stagnation point, and show that the stagnation pressure is equal to the sum of the static pressure and the dynamic pressure terms. All of the kinetic energy is essentially being converted into pressure energy at the stagnation point. If we add an outer tube which is sealed at the end but has holes further downstream, the outer tube will measure the static pressure of the fluid instead of the stagnation pressure. These two pressure measurements give us all of the information we need to determine the velocity of the flow. Another flow measurement device that uses Bernoulli's equation is the Venturi Meter, which is an instrument used to determine the flow rate through a pipe. It works by measuring the pressure drop across a converging section of pipe. Say we want to determine the flow rate, Q, which is the velocity multiplied by the pipe cross-sectional area at point 1. We can easily rearrange the pressure drop equation we derived earlier when we looked at a change in diameter to get this equation for flow rate. All we need to know is the dimensions of the Venturi meter, the fluid density, and the pressures P1 and P2, and that allows us to calculate the flow rate. The Venturi meter has no moving parts and is a very simple and reliable way of measuring the flow rate through a pipe. The diverging section is longer than the converging section to reduce the likelihood of flow separation and keep energy losses low. Let's look at one more example where we can apply Bernoulli's equation. Say we have a beer keg, and we want to calculate how fast beer will drain when we first open the tap at the bottom. All we need to do is define our 2 points along a streamline and apply Bernoulli's equation. It's a gravity-fed keg with a vent at the top, meaning that it's not pressurized. The pressure at both points will be atmospheric, and so the static pressure terms cancel each other out. We can also assume that the keg is large enough that the fluid velocity at point 1 is close to 0. If we rearrange Bernoulli's equation and define the height between the beer level and the tap as h, we get this equation for the beer velocity out of the tap. Those were a few examples of cases where we can apply Bernoulli's equation to get some valuable information or to solve a problem. But to use it correctly, it's important to have an understanding of the limitations of the equation, which arise because of how it's derived. There are several different ways Bernoulli's equation can be derived. It can be derived based on conservation of energy, by considering that the work done on the fluid increases its kinetic energy. Or it can be derived by applying Newton's second law, which involves determining the forces acting on a fluid particle and applying F equals ma. Although I won't cover either derivation here, they do both make some assumptions that we need to be aware of, since they limit how we can apply the equation. Firstly, the derivation of Bernoulli's equation assumes that flow is laminar and that it is steady, meaning that it doesn't vary with time, like this. Next, it assumes that the flow is inviscid, meaning that shear forces due to fluid viscosity are negligible. This assumption is needed because viscosity would result in a dissipation of some of the fluid's internal energy, and so the idea that energy is conserved along a streamline would no longer apply. And finally, the derivation of Bernoulli's equation assumes that the fluid behaves as if it's incompressible. This is usually valid for liquids, but might not be for gases at high velocities. All three of these assumptions need to be valid if you want to apply Bernoulli's equation. Adapted versions of the equation which can be applied to unsteady and compressible flows do exist, although they're a bit more complicated. Being able to recognize when Bernoulli's principle is at play, or when Bernoulli's equation can be applied to solve a problem, is a powerful tool in any engineer's arsenal. If you'd like to see a few more real-world examples of Bernoulli's principle in action, you can check out the extended version of this video on nebula. Creators like myself. It's home to some of the best creators.
Okay, walaupun tadi even though the explanation might be a bit longer than actually we will discuss in details what you have watched from the video, but can anyone want to say something relating the content of the video, what you get from the video? Kanzu 106. Are you there?
Yes, sir. Hello. Hello.
Yes.
Hello? Can you hear me?
Yes. Clear.
So about the video, sir.
Mm-hmm.
Yeah. So what I get from the video is the application of the Bernoulli's law.
Mm-hmm.
Yes, and which it's similar to like the Newton's second law, and the liquids which applies to the Bernoulli equation needs to have three apa namanya?
Equation.
What requirements? Yeah, requirements.
Yeah, three requirements.
Yes.
Okay, good. Okay, but from the video, you can see that basically the Bernoulli equation are representing the energy balance. If you pay attention to the video, there are three components, right? Can you maybe other student still remember? Karunia Bintang, are you there?
Yes, sir.
Okay. Do you still remember what kind of three component in Bernoulli equation?
Static pressure.
Pressure, okay. There are always three parts, right?
Kinetics or kinetic energy.
Okay, kinetic, correct.
Potential energy.
Yes, the last one is potential. Okay, good, thank you. So basically, we will discuss about the Bernoulli equation and also the application. Maybe in our next class, but I hope you get the first grasp that this is the component of Bernoulli. Yeah, Bernoulli is Bernoulli equation is basically energy balance equation, where the component is the in the video it mentioned that all are form of pressure, right? But one is direct pressure, the second one is the kinetic pressure, and the third one is the potential pressure. So the equation written in the video is basically in pressure unit. So all are in pressure unit. Pressure unit means Pascal, even though the parameters involved for each type of pressure is different. But you can check, maybe you can rewatch the video again, and then you can check whether the unit of each pressure, kinetic, and potential is all are in pressure unit. But in general terms, Bernoulli is energy balance. It means it will deals with the pressure energy, the kinetic energy, and potential energy. And same with the mass energy will also have what we call energy conservation law. So the total will be constant. That's why in Bernoulli, in the video, you watch that all the totals in one point and the totals in second point is always the same, because that's the concept of energy conservation. The total energy of the system is always constant, but it can be transformed from one energy to another. So in the video, it was mentioned that if the potential energy is constant, yeah, the pipe is horizontal pipe, doesn't have difference in height. It means if the velocity contribute to the kinetic energy, pressure, it will be contribute to the pressure energy. So if the kinetic energy is increased, the velocity is increased, then the pressure is decreased. That's, they said, is counterintuitive, because maybe for the example, if you have a hose with the if you have the hose with the water flowing, ya, Anda punya selang, terus ada airnya gitu. If the water cannot reach more distant places, what will you do? You will pinch the hose, right? Ya nggak? Kalau misalnya ada lagi mungkin siram-siram tanaman, you're watering the plants, and then you need to reach to more to the plants that further. Then what will you do if you do not have the sprayer? Then what will you do is you pinch the hose. Pinching the hose means you decrease the diameters. Decrease the diameters means you increase, yeah. Decrease the diameters, it means you decrease the area, right? And then it means you increase the velocity. Because please remember what we have just learned, this one, right? This is always constant. By decreasing the area, by pinching the hose, then you will increase the velocity. That's why the water will flow further, because the velocity is higher. However, the pressure is actually decreasing. Okay, and later we will see that the energy level of the object will be expressed as the relative energy compared to the basic or datum energy level. I used to call it a baseline. Ya, jadi ketika Anda nanti menyatakan energi level, ya, tingkat energi, itu biasanya adalah sebagai tingkat energi relatif. Relatif terhadap apa? Terhadap baseline-nya. If, for example, if the potential energy you have ground, then if the pipe is like this, then the potential energy here and here will be different relative to the baseline. Okay, I think it's enough for now. Do you have any question? Okay, if you have no question, then we can have our discussion continued on Tuesday. Thank you so much and good afternoon.
Yes, sir.
Thank you very much.
Thank you, sir.
Thank you very much,
sir.
sir.